Amherst. Chemical Engineering, Polymer Science 757, Polymer Rheology, H.H. Winter, Lecture 16a. Cross-linking polymers undergo an interesting transition at the gel point, where they go from a sol, from a liquid, to a solid. We can detect this transition by measuring the relaxation modulus. So if you plot relaxation modulus versus time in a log-log scale, the material at the gel point follows a power law. So the relaxation modulus is given by a constant, let's call this S, times t to the minus n. It doesn't relax in a single exponential function. It really follows that simple relation. Now, in the material before reaching the gel point, in the liquid, in the sol, you will have a relaxation modulus which decays, being curved downward. So we would call this the behavior of the sol. And in the material beyond the gel point, the material the stress will not be able to relax. The modulus has a constant value, which is leveling off here. This is the so-called equilibrium modulus, and this would be the so-called gel. And the material at the gel point, where the conversion is equal to the critical conversion, P equal to PC, is called the critical gel. Now, the dimension of S is Pascal times second to the n. Therefore, the gel strength, S is often decomposed into a modulus. Let's call that G0 times a characteristic relaxation time, lambda 0 to the n. We have to specify what this modulus is and what this characteristic time is. So far, we only know that this is one constant, and we could determine that constant if we have data to plot this modulus. At short times, there will be a transition to the glass. So at a shortest time, there will be a transition to glass and then having a very high modulus. We are neglecting this glass transition in the moment, but we could say that this modulus is valid above a certain shortest time for the glass transition and up to an infinitely large time, because the spectrum is really diverging at the gel point. Remember, the longest relaxation time at the gel point is infinitely large, and that's expressed by this range here. If you introduce this format, you could rewrite the modulus as a relaxation modulus as a constant modulus times t over lambda 0 to the minus n power. And that's the relaxation modulus. Now, from this, I would like to calculate the relaxation spectrum with you. And to do that, we look at the definition of the relaxation spectrum. The spectrum, the relaxation time spectrum, gives us the modulus. So if you have a relaxation time spectrum integrated from 0 to infinity over all times, times e to the minus t over lambda, d lambda over lambda, then, well, this is just a definition. The defining equation, it relates the relaxation modulus with the relaxation spectrum. Now, this type of integral is a so-called Laplace transform. We could say h of lambda divided by lambda has a transformation g of t. This is the so-called Laplace transform. we know that g of t is given by t to the minus n. And we would like to look now for the Laplace transform, which gives us t to the minus n. And I prepared some material here. I brought this with me here. This is the general definition of the Laplace transform f of t. Now, a typical transform pair can be looked up in a table where t to the minus n is the function after transformation. And the kernel function f of x, then, in this case, is x to the n minus 1 divided by the gamma function over n. That's a tabulated solution which you could pick up. And we are really looking for a solution of t to the minus n here. Now, we insert this pair of transforms into the above integral and find that t to the minus n is equal to an integral from 0 to infinity of x to the n minus 1 divided by the gamma function times e to the minus tx dx. Note that we are not looking for x. We are looking for a quantity 1 over. We are looking for t over lambda here. So let's replace x with 1 over lambda. Introduce a substitution. Then dx over x, we have to extract 1x here. Dx over x is equal to minus d lambda over lambda. And the lower bound, when x is equal to 0, lambda will be infinite. And at the upper bound, if x is equal to infinite, lambda will be equal to 0. So this, in the new case, the integral will have a minus sign from here and will go from infinite to 0, or we are interchanging the order to have the result t to the minus n is then given by this integral 1 over lambda to the n divided by gamma function e to the minus t over lambda d lambda over lambda. And we will introduce that now in our solution here. So we know now that we can write our relaxation modulus as an integral from 0 to infinity of g0 times lambda. This was to the minus n, and here we have over lambda 0, so we can write lambda over lambda 0 to the minus n already. And we accommodate the gamma function, 1 over the gamma function, times e to the minus t over lambda d lambda over lambda. And by comparison of this result with the other function over here, we find that the relaxation spectrum, the continuous relaxation time spectrum, is given by the characteristic modulus of our system divided by the gamma function evaluated for n times lambda over lambda 0 to the minus n. And this spectrum now is valid above our shortest time, lambda 0, up to infinity. And this is the spectrum which has been found by Chambon and myself. Okay, so that's the fingerprint of the material at the gel point. And this is the spectrum which gives you a relaxation modulus which follows a power law like here. And there's no singularity involved. But we still have to specify G0 and lambda 0 from maybe some experiments, or if there would be a theory, it would be nice to get this additional information. Let me plot the result of that derivation. I mentioned it before in the last class. It's a spectrum, h of lambda, which follows a power law going to infinity. It's describing the terminal behavior of a polymeric material. Beyond a shortest time, here, the lower cutoff, the glass transition will be described by a power law, for instance, as suggested by Tobolsky. That's a very nice description. We could include at that time now even the transition, the glass transition, by taking the two power law, taking the crossover of those two power laws. We could say there's one power law for the glass transition. This gives us an asymptote for low lambdas, and then there is the critical gel behavior, which gives us the asymptote at large lambda values. We could superimpose those two on a log scale. We could just say that lambda is given by a first power law multiplied with 1 plus a second power law function here. Note that at low lambda values, this quantity vanishes compared to 1, and we are just ending up with a constant times lambda over lambda 0 to the a. So this is the glass transition behavior. That's the asymptote at low lambda values. Therefore, the exponent a is minus ng. That's the exponent describing the Tobolsky spectrum. So we know this exponent. Now let's take the high lambda asymptote, which is given by the critical gel. And there we know that the exponent should be minus n. Now our initial equation here is changing in the following way. The second term here has lambda over lambda 0 much, much bigger than 1. So this term is dropping out, and we just have a power law where lambda appears with exponent a plus b. So we have lambda over lambda 0, exponent a plus b. And this exponent is given by the critical gel. That's minus n. And the front factor now is given by the modulus divided by the gamma function as we just calculated. That's what you just saw. So everything is determined, and we could write down the spectrum for the glass transition plus gelation given by this type of power law. That's a linear superposition. It's just a heuristic approach where we know that the asymptotes are accommodated. The quantitative agreement in this range has to be studied and has to be shown that this is okay, and we haven't done that so far. But that would be a simple way of accommodating the transition, which we shouldn't neglect. In the beginning, I often had the question, what happens to your gel at very short times? And the answer is, to the gel, you have the same thing happening to, as you know, will be happening to a liquid. If you put a very short-term load on a liquid, it behaves glassy. And then if you put a very short-time load on an impulse-type load on a solid, it also behaves glassy. So it's the material in between, the gel, has exactly the same transition at very short times. So there's no difference. From those functions, which you just calculated, from the spectrum, we can calculate all linear viscoelastic functions you can imagine. Not only the modulus, but you could calculate, for instance, the retardation spectrum. But I'm not going to go into those details. So this is the spectrum which describes the material at the gel point and goes from the glass transition to infinity. The modulus associated with that is described by the simple format. Because of this choice here of the modulus, we are inserting a gamma function here. We can choose one of the functions in a simple format, like I did here for the modulus. And if you do that, the conversion, as shown on the blackboard, gives you this gamma function. You could choose a very simple spectrum here, and then you would get some gamma function term in the modulus. So there's no miracle about that. Here's the range of validity of both. You could insert now h of lambda in the formula for g prime. Remember, that's the integral of h of lambda times omega lambda squared divided by 1 over omega lambda squared times d lambda over lambda. You integrate that, get a complete solution. You get a complete solution when neglecting the short time behavior. You would just get then the power law range. See, this is just the power law. It doesn't show the lower cutoff, or the high frequency cutoff in this case. And g double prime you also can calculate from that. Tan delta, the ratio of the two, is interesting here to note that omega to the n is dropping out. And tan delta is independent, the loss tangent is independent of frequency. And we will use that for determining the gel point in a moment. You can calculate the magnitude of G prime, G double prime by just getting the complex modulus. It's just the front factor. And it's omega dependent. And from that, you calculate the dynamic viscosity. It's 1 over G star. And if you insert everything, it's a gamma function of 1 minus n times the modulus times the characteristic time the omega dependence here. There's omega to the lambda 0 times to the power n minus 1. We will use that in a moment. So that's an interesting result, and we can pose many questions. The most obvious question is, where does it all come from? Why does the gel behave self-similar? Like we see in this experiment. And there are many possible answers. One would be that the molecular weight distribution is very broad, and it also follows a power law near the gel point. So there's a possibility that a power law molecular weight distribution would give a power law relaxation time spectrum. We don't know. That would be something to explore. Also, the molecular structure is very complicated. It's a so-called fractal structure, and when you calculate the relaxation behavior of molecules which are not linear or stars also, but molecules which have a fractal structure, you will find that they follow a self-similar relaxation behavior. Muthu Kumar has done that some years ago in '85. So he had predicted power law relaxation behavior from first principles by using a fractal self-similar structure of the molecules. So maybe that's the origin, or combination of all of those. That's something to explore. The theory cannot predict in all details what we are seeing. A percolation theory predicts the self-similar relaxation behavior, at least in a conductor capacitor network. But it's still not the derivation for the molecules in a 3D case where you have flexible chains connecting the spaces on a lattice or so. So it's not completely clear. We can, for instance, not predict the value of the relaxation exponent n. There are some theories which say that there's a unique value for n. There only should be one. But the experiments tell us there's a whole range of n values. So there must be something missing in the theoretical approach. OK, so where does this pattern come from? We should look at the relation of n, which is an exponent for the behavior at the critical state at the gel point, relation of that with the classical critical exponents. We will do that next. And we also should look at the divergence of the longest relaxation time, see what's the critical exponent of lambda max, not just of the viscosity or the modulus. So what is that? And then, since we are looking at behavior near the gel point, what's the nearly critical gel? What's the behavior not directly at the gel point, but in close vicinity to the gel point? So this is something to discuss. Then we will look at the effect of molecular parameters. What does, for instance, change of molecular weight do to our gel behavior? We will change stoichiometric ratios, so the cross-linking statistics will be altered. Or we will put entanglements in the system by taking long chains which we are then cross-linking. They are already entangled. And then we put some diluents in there. We're swelling the chains and see what's happening to the gel transition. Gels are very soft materials, and very often swollen materials are looked at near the gel point. Then we would like to know what's the large strain behavior. Gels are very soft, so what happens when we deform them, expose them to large deformations. And also, we will look at physical gels. Instead of having crosslinks formed by a chemical bond, we can have crosslinks by some physical interaction, ionic bonds or glassy regions, crystalline regions, and many different possibilities for forming physical gels. And the question is, do they perform in the same way as the chemical gels? And you will see they do. They follow exactly the same pattern. So let's take those subjects up one by one. First, I would like to look at the critical exponents with you. The critical exponents describe the behavior in the approach of the gel point. They will describe the viscosity in the approach of the gel point and the relaxation or the equilibrium modulus in the approach of the gel point from the other side. So the schematic is something like this. The viscosity diverges near the gel point, and the divergence here is given by a power law. The viscosity is proportional to the distance to the gel point. And actually, as the distance gets small, the viscosity gets big, so we're having 1 over, and the critical exponent in this power law is S. It has, this is a material characteristic property, or maybe it's a universal exponent. We don't know. And in the same fashion, the growth of the modulus in the vicinity of the gel point is described by a power law, and the exponent is Z. So those are our typical exponents which describe equilibrium properties in the vicinity of the gel point. There's extensive literature on this subject by Stauffer and by Dejean, and literature on critical phenomena where you could see where you have this type of phenomenon being discussed. Now let's relate this to the gel behavior, and I would like to go to the viscosity now, because you saw that in the sole, the divergence of the characteristic property is given as the divergence of the viscosity, right, of the zero shear viscosity. So now I plotted the complex viscosity here for you, which is really defined by G prime, G double prime. If you take the square of each, sum them up, and divide it by omega. So the same old data set in dynamic mechanical experiment will give you the viscosity. The limiting case in this case, in the terminal zone, is the following. If omega goes to 0 and you have a liquid, then the viscosity will simply level off, and the viscosity value here is equal to the zero shear viscosity. This is this level. And in the case of a solid, the terminal behavior is given by a constant slope here, and the slope is -1. The viscosity is really defined by the equilibrium modulus divided by omega. So we have a terminal zone given by this type of slope, -1. For relating things to the critical exponents, we will need the zero shear viscosity, and we will need the equilibrium modulus, and describe those in the distance from P minus PC. There's a question, or no? It has been resolved. Okay, so the typical fingerprint of our gel is the following. The material at the gel point, the critical gel, has a relaxation behavior like this, power law relaxation behavior. The slope is really given by omega to the n to the -1. Omega to the n -1 is the slope here, because we are dividing here by omega, and those guys go with omega to the n. And before the gel point, we have a viscosity function like this, and beyond the gel point, we have a viscosity function like that. Let's start with the viscosity function before the gel point. We're talking about the sole. And we will use the behavior at the gel point as a reference state. We have new information. We know what the relaxation behavior is at the gel point. And with that information, we can describe now, say, the longest relaxation time, for instance, of this material. And we can do this in the following way. We take the viscosity of the sole, the material before the gel point, and the terminal zone is given by zero viscosity here. Now, with increasing extent of reaction, this zero viscosity will increase, and you will have a high level, and then it will go down like this, and it will become higher and higher. So this growing viscosity is a measure of increasing extent of reaction. We can intersect the gel, the curve for the gel. This is the curve for the critical gel. Here I listed that. The viscosity, dynamic viscosity, is given by a constant times omega to the n -1. This constant is, we defined that before, so let's just take it as a constant here. And this curve now is intersected with the value of the viscosity and gives us a intersect frequency. And 1 over that frequency will be defined as the longest relaxation time. That's our choice, or that was my choice. There was no definition for that, so I've just defined the longest relaxation time as 1 over this intersecting frequency. And as the viscosity increases, the intersect moves to lower and lower frequencies, and that's the typical behavior. The relaxation time assumes larger and larger values. Let's do that mathematically. The zero shear viscosity is diverging with the distance from the gel point, as we had before, following with the critical exponent s. And the intersect now is given by putting eta 0 equal to eta star. So we have eta 0 is equal to the constant times the frequency at the intersect times n to the minus 1. And this frequency at the intersect has been defined as 1 over the longest relaxation time. We rearrange that to express the longest relaxation time in terms of eta 0. Now eta 0 goes with this distance from the gel point, and we find that lambda max is given by the distance from the gel point to the power s over 1 minus n, and its negative sense, it's diverging. This is diverging as this becomes very, very small. So that's why we need the negative exponent. Actually, it comes out of the calculation. So we know now the critical exponent for the relaxation time in the sol, while the sol is approaching the gel point. Let's do the same thing from the other side. Let's calculate the critical exponent of the longest relaxation time in the approach to the gel point in the gel from the solid side. The fingerprint is shown here. The critical gel, again, is our reference state. And the terminal zone in the critical gel behavior gives us slope of minus 1. So eta star is just the equilibrium modulus over omega. And the equilibrium modulus is given by the critical exponent z in the approach of the gel point. P minus Pc is just the distance from the gel point. We combine this here. We introduce GE into eta star. And we also say that this curve here is intersecting the gel behavior, and we find an intersecting frequency, which is 1 over the longest relaxation time. And we calculate the longest relaxation time as the distance from the gel point to the minus z over n. And if we come from the positive side, from the solid side, as we make this very small, you can see that lambda max is diverging. So from these formulas, we derived a relation for the divergence of the relaxation time from both sides, in the sol, in the gel. In the sol, the relaxation time diverges here with this exponent. I'm just summing up what we did so far. And in the gel is diverging with that exponent. And basically, those derivations describe the asymptotes for P, the extent of reaction, going to Pc. There are no assumptions involved in this case. It just we just took a reasonable definition for the longest relaxation time, and I think there's no problem with that. So we can use this result as an experimental observation. And now comes our first assumption. We would say that the divergence of the longest relaxation time is symmetric on both sides. And some theoreticians tell me it has to be like this. Other people say no, it cannot be symmetric on both sides. So I don't know. So this is a real assumption. And let's take that assumption in the moment. Let's say take symmetry, and let's say that those exponents are equal. And if they are equal, then you can evaluate n. You just set them equal, and then you evaluate n in terms of s and z. That's a very interesting result. You can already say that if n is a material parameter, if that changes from critical gel to critical gel, and we know it does, then z and s cannot be universal exponents. And that has an impact, a very deep impact on polymer physics. So this, just by doing a few harmless experiments, we're causing lots of trouble here to, to basic physical arguments. Okay, so this is a first interesting result. And then we also can eliminate from those exponents, we can eliminate n, just saying that they're equal, and we would say that this exponent is equal to that exponent, and you will find that this is only true if the exponent is s plus z. Or you can put this exponent in here, and here you will see that it solves the problem. So now we know something, a second interesting result. We know that the longest relaxation time, this is lambda max here, lambda max, diverges with a critical exponent which has a value s plus z, the sum of the two critical exponents which we had before. It's not a new critical exponent. And I think that's a very interesting result. And again, it's an experimental observation. It's not biased by any preference to a theory. You might like percolation theory, or you might not like percolation theory. This derivation is an independent result which can be used to evaluate theories and see whether they can fit this type of behavior. With that with this information now, knowing the divergence of the longest relaxation time, it's actually very hard to measure those critical exponents. So we kind of know that, but more experiments are needed to pin down the results. The problem in measuring the behavior near the gel point is, first, the exact determination of the gel point. We can do that now. Since recently, by knowing the relaxation behavior at the gel point, we don't have to extrapolate. But when you look at the data in the literature, they are all extrapolating. So they don't have an exact value of PC, and they have some estimate of the difference P minus PC, and then they can get all kinds of power loss in the vicinity of the gel point. But now we can measure PC exactly. So I think there's a good hope now to measure critical exponents, and we can assume for the time being that we know what those exponents are for our sample, because we will be able to measure them. And if we have them, we can describe now the behavior in the vicinity of the gel point. This is this type of region. We would call those materials nearly critical gels, because they are, in their behavior, they are very close to the critical gel behavior already. We can write down the relaxation spectrum of a nearly critical gel. We could say it's, again, the same power law spectrum as before, power law spectrum, which has a glass transition at lambda 0, but then it has an upper cutoff. The longest relaxation time is finite in the material near the gel point, but we know that this lambda max, that this cutoff time is given by the distance from the gel point with that exponent, with the critical exponent. So we are describing that here. And we could formulate now the spectrum by just taking the spectrum as we had before, but having lambda going from lambda 0 to the maximum relaxation time. We have an upper cutoff introduced, and that's describing the behavior very nicely. You can use that spectrum to calculate a relaxation modulus for the sol by just introducing this. We're having this Laplace transform here. The integration goes from 0 to the longest relaxation time. And this is h of lambda we have. So this is where we introduce the upper cutoff. And in the gel, you use the same function. You have the upper cutoff introduced here. Plus, you have to add the equilibrium modulus to describe the solid behavior. With that, it would be the liquid behavior. And here, now this is where the symmetry is visible again. This was our assumptions. If we have the same function on both sides, we will see the symmetry coming in here. The evolution of the dynamic mechanical modulus is also interesting. G prime, how does it evolve with extent of reaction in a cross-linking system? Let's assume let's choose a material which cross-links very slowly so that we can measure G prime, G double prime as a function of time. the resulting modulus of that system is given by this type of behavior. G double prime is dominating the early behavior. Very low extent of reaction. The parameter here is the cross-linking time. So we have a liquid which has no elasticity. It increases, the G double prime, the loss modulus increases as the molecular weight increases. But then the elasticity comes in and takes over. And at the end, we have a solid which is really has a dominating G prime and very small G double prime. For a long time, there has been a myth saying that where the liquid behavior, saying G double prime characterizing liquid behavior and G prime characterizing solid behavior. It's not completely true, but that's where it comes from. So there was a myth that where those two are crossing, that this is the gel point. We don't have any singularity in this experiment. Just go at constant frequency. We're probing one specific relaxation mode, basically, which corresponds to that frequency. And we're probing the strength of that mode. In the beginning, it's really dominated by viscous behavior. And at the end, it's dominated by elastic behavior. That's all we are saying. And here, they are balanced. And the myth was that this is the gel point. And it turns out that this is not true. Now, there are many people who religiously believe that this is the gel point. And you will not be able to convince them that it's not the gel point. And it's so I guess they will just continue believing that. But the gel point occurs at the instant when G prime and G double prime are given by power law behavior, or where 10 delta is independent of frequency. We will look at that. So from our experiment here, we would not be able to see where the gel point is. We would need a more complete data set over wide ranges of frequency to distinguish the power law behavior as it comes in. There are actually systems which are very elastic in the beginning. So at a given frequency, those materials are liquid in the beginning, but their G prime is higher than G double prime. And then as those systems undergo gelation, they will never have a crossover of G prime, G double prime, but they're still going from liquid to solid. It just doesn't make sense to take this crossover here as the gel point. Now, for some materials, the gel point is very close to this crossover. So for technical purposes, to get a first estimate, you might use that. But just keep in mind, it is not the gel point. You have to do some more work to identify that. So far about this very important point. I got a sore throat already talking about this for so often. Now, we take the magnitude by just taking the complex modulus, magnitude of G prime, G double prime combined, as a function of reaction time, really expressing G prime, G double prime in just one term here. Now, if we express that at zero viscosity, zero frequency, then this modulus does not have any contribution from the viscous part. It's only having a contribution from the elastic part. So the modulus will gradually increasing, and this is like increasing like the increase of the equilibrium modulus. But as soon as you go to a finite frequency, you're picking up a viscous and elastic response, and then it's gradually coming up and getting a higher result. And at a reasonable frequency, you have the viscous part coming in the same way as it comes here. Okay, so that would be the typical growth of the dynamic modulus for different frequencies. And the slope here at the gel point is decreasing when you go to higher and higher frequencies. It has an infinite slope here at the transition. And if you plot now the slope here, this is the slope here. This is the slope of G star at the gel point, evaluated here at the gel point. I'm taking this. Thought I had some scratch paper. I'm putting on the tangent here onto this curve here and measure the slope, and this tangent goes to infinite as omega goes to 0. And amazingly, it has a power law character. And the slope is smaller and smaller as we go to lower and lower frequencies. And the exponent here, this goes with omega to the power. This changes with omega to some power. And the power is minus kappa. And kappa is 0.2. And surprisingly, we found 0.2 for all the samples we were looking at. So somehow the dynamics, how the structure is developing when material goes through the gel point, seems to be the same for all systems, even if they have critical exponents which change from material to material. The way the gel develops seems to be some universal fashion, and we have to learn how to understand that. So there are interesting areas to pursue. The evolution of the spectrum can be determined by taking, say, frequency sweeps. You measure G prime, G double prime over many frequencies, and the sample is cross-linking while you're doing that. So within your frequency window, you get data now in the liquid state where you get closer and closer to the gel point. And your relaxation pattern is changing as the molecular structure of your sample is changing. And there's a proposal now by Adolf and Martin where they say that in the soul, the relaxation modulus is given by this power law spectrum, here by our spectrum, multiplied with some cutoff, some exponential function. And they're saying all data might fit into the same relaxation pattern, have the same modulus, only the cutoff is changing as you're approaching the gel point. So if the shape is the same, then you can use data in the solid state at different distances from the gel point and shift them all into each other to get representation of the spectrum closer and closer to the gel point and to over a wide time range by having a characteristic time, lambda max, changing during the experiment. And the same thing in the gel, you again would have a characteristic time which changes the characteristic behavior of the material typically, and you can scale your results with that, and you can shift all the data into each other. And this is the spectrum which he calculated. Maybe we can just magnify something like this. Yeah, those would be, I have to show you upside down here. This would be now a set of data taken in the soul. This is early data of G prime, G double prime. This would be late data of G prime, G double prime. And Adolf and Martin, could you focus a little bit, please? And they were shifting those data now into a set of master curves over a very wide frequency window, which they could never measure in reality. And this would be the typical fingerprint of G prime and G double prime in the system, or vice versa. And they do the same thing here for the material in the gel. This would be typical gel behavior, and close to the gel point, everything comes down, and they're fitting all of this into a set of curves. This is G prime, and this is G double prime at the gel point. In this case, they use very small low molecular weight, and they find a slope of 0.7 to describe all this behavior. So let's take a break here at this time and look at the effect of molecular structure. Take systems with different molecular weights and see what's the behavior. Change the geometry and things like that. University of Massachusetts, Amherst, Chemical Engineering, Polymer Science 757, Polymer Rheology, H.H. Winter, 16B. The molecular structure has a large effect on the properties of polymer gels, and we should look at different effects here. And in all cases, we will use an experimental approach. Since we don't have a theory describing the material at the gel point in a quantitative fashion, we certainly could not get any answers about the effect of molecular weight or molecular weight distribution or diluent and all those phenomena on the critical gels. So we are reverting that. We continue looking at materials by just taking a well-defined sample and studying that sample in some experiments and then analyzing the results and seeing whether everything is self-consistent. So that's the approach we will be taking, and we will look at phenomena of stoichiometry, changing the stoichiometric ratio. We will change the molecular weight of the precursor. See, the viscosity is dependent on molecular weight of a material. The modulus of a material depends on the molecular weight, the modulus of a cross length. So why not the material at the gel point also? And then we look at the effect of diluent, making a gel softer by putting a solvent into that system. In all cases, we will make gels. We will explore the gelation behavior by making a gel, putting it in the rheometer, and measuring its relaxation behavior. The fingerprint at the gel point will be the following. We will have G prime and G double prime following a power law. The spacing is given by the slope. We saw that last time, taking Amherst-Kronig relation. And we know that the slope has to be the same. So when you take the ratio of G double prime over G prime, then you immediately see that 10 delta, the ratio of it, is independent of frequency. So that's the fingerprint of a material at the gel point. Note that 10 delta has to be constant in the approach of omega going to 0 in the terminal zone, not somewhere at high frequencies. It has to be constant in the terminal zone here. And the same thing, this power law should be extending into the terminal zone. That's very important to note for the definition of the gel point. But now let's try to reverse that and ask the question, given a material which shows 10 delta independent of frequency, say somebody gives you experimental data. Now, is that material exhibiting power law G prime, G double prime? If we have this as a power law, we certainly get a flat curve. But can we reverse the argument? Answer is no, but I want to derive that with you by going through these equations. So let's take an arbitrary function, f of omega. Let's take this function and saying that G prime is described by this function. It's any function f of omega. Then to obtain 10 delta independent of frequency, G double prime has to follow the same function, but it can be modified by some constant. But that's the condition to obtain 10 delta. And the question is, what's f of omega? We can go to the Amherst-Kronig relation and insert f of omega for G prime and for G double prime, which gives us f of omega equal to the typical function here for Amherst-Kronig, equal to f of x times a, because we're putting G double prime in here and we have G prime there. Okay? That's the form we have so far. We can substitute now x over omega, we would call y, our new integration variable, and rewrite our integral, which we had before. This was the integral which we had. F of omega is given now by some function as function of y. Now, x is equal to y times omega, so we have a function f of x will be f of omega times y. and the constant is over here, and we're integrating 1 minus omega squared. And since all the omegas have been pulled out, it's here this omega square is canceling with that. But still, we have a function of omega here, and after integration, this also should be a function of omega, or it should be the same function, f of omega, multiplied with maybe a constant is coming in, which of course should be, a should be chosen such that all of this is 1. This should be 1 times f of omega. Now, we can choose a function f of omega, which should be very specific. It should be really a factorial type function. It should be f of omega times g of y. And when introducing this function here we are. We are introducing this function in this integral up here, and find then here f of omega canceling with this f of omega, so this will be 1 equals to some number containing a. Right? And a was our 10 delta. This was just the material-specific value. So we can evaluate, in this case, 10 delta, and a is given now by this condition. So we realize, now going back to our initial function, that a cannot be anything arbitrary. It's somehow prescribed by the relation of the two things, and it really, a depends on the choice of f of omega, basically. Because for evaluating a, we will use not f of omega, but we will choose g of y, which depends on our initial function. Okay? So we know that the function f of omega y has to be of this format, f of omega times g of y, multiplied with some constant, which we don't know yet. And certainly, if f of omega is a power law, that's what we are using all the time, then the relation is satisfied. But I'm sure you will be able to find another function, f of omega, which also satisfies this constraint and will give us 10 delta being constant. So I would be careful. If we just have data giving us constant 10 delta, even in the terminal zone, it doesn't necessarily tell us that we have a power law in g prime, g double prime. But so far, with all our experiments, that's what we got. They always find this power law. Maybe the power law behavior is inherent in all our samples, and then we find 10 delta constant in the whole spiel, the whole variation of that. Okay? But in an abstract sense, if you just get 10 delta being constant, you don't know whether you're really in a power law state. We use that information anyway, because in our case, we know that 10 delta constant gives us the gel point. Look at the modulus of a material which goes through the gel point. This is a little before the gel point. This is at the gel point. This is beyond. It's very hard to distinguish any power law behavior at different times. We wouldn't know which one is the material at the gel point, which is the solid, which is the gel. But if you look at 10 delta, or we just plotted delta here times 2 over pi, which is a plot looking equivalent, that's flat at the gel point, and it is curving up in the sol, and it's curving down in the gel. So 10 delta is very sensitive. It's a most sensitive experimental value anyway. So it's very sensitive to tell us where the gel point is. We often will use data. Since I'm talking about this, we will use data where we look at 10 delta at a function of reaction time, as a function of reaction time. And we will plot 10 delta for different frequencies. This would be the first frequency, second frequency, and let me turn it around here. Third frequency. If you just do this at a number of different frequencies, then the instance where 10 delta is independent of frequency, say omega 1, omega 2, omega 3, omega 4, where this is independent of frequency, that is the gel point. So we have a method of finding the gel point in the sample without stopping without stopping the material. It's much easier than before. In the beginning, we had to stop our cross-linking reaction, had to use this Pompeii technique so to find the gel point. Now, look at this. If you have data like this, you don't even reach the gel point with your material, you can already take this information, and you know that in 5 minutes, you will be at the gel point. So you can use that technique even to monitor an evolving structure in the material. You might stop your reaction before reaching the gel point. That has been used for making toner materials, which should be close to the gel point, should be highly cross-linked, but should never reach never solidify. Okay? So it's a very powerful method, and it is the first method and the only method I know which gives the gel point directly. All other methods are extrapolation methods, and the results from this technique agree with the other techniques. But we will never be able to confirm this exact measurement, this direct measurement, because of the difference in those approaches. Now we can make many different gels, and Jim Scanlon did those. He used a medium-sized prepolymer. It's a PDMS chain of 10,000 molecular weight about. He made gels by changing the stoichiometric ratio. That's the molar concentration of cross-linker ends divided by the molar concentration of reactive chain ends. So he's changing those. In the case of balanced stoichiometry, if this is 1, you would get the most perfect network structure. So he's including that. And he has now the front factor. We're looking at the parameters S and N, those two constants. Now, S is increasing with increasing stoichiometry, and N is somewhat decreasing. If S is large, then the gel is very stiff. It's the gel strength here, S, if that's very large, have a very stiff gels. Also, if N is very small, in the limit of N equals 0, this would be just a Hookean solid. Right? So if N is very small, it approaches regular solid behavior. So a stronger front factor goes along with a low value of N, and there's actually a mirror image of the two. They are not changing independently, they're coupled. Jim Scanlon did the same experiment with a high molecular weight sample, about 50,000 molecular weight. Again, S is increasing with stoichiometric ratio, N is going down, going through a minimum here. And again, there's a mirror relation between the two. He added some diluent to his polymer. He took a medium strand material and added diluent. This would be pure polymer. He has the strongest material. S is largest. And then he goes from 100% polymer to 0% polymer. He just adds 10,000 molecular weight chains, the same change as he has for making his cross-linking systems. He adds more and more of those, but they don't participate in the cross-linking reaction, so the network is getting softer and softer at the gel point. So S goes down, and as a mirror image, N comes up in this case, and the softer gel has a large N, so it's relaxing very quickly. So dilution makes our material even softer, and we can tailor the gel properties by changing the stoichiometry or the molecular weights and all this. It's really up to us. Now comes the interesting result. You already noted that S and N are not independent of each other. They are coupled. So Jim plotted S over N in a semilog plot and found this type of relation. And he and he found a straight line in here. And for the medium strand, he found also a straight line. Somehow, all samples for one group of material are connected by this straight line, which is characterized by a slope given by the characteristic time and a front factor G0. So just two constants describe whole groups of gels. And the same thing here. And we know now that we should determine G0 for our material and lambda 0, those two characteristic parameters. And then by changing the stoichiometry, we would get different n values, changing n, but we can predict then the variation of our properties for those gels. So this can be used for making gels which are softer or harder in materials in the vicinity of the gel point. Let's look at the next molecular parameter, and then we can sum up all of those. We would like to change the precursor molecular weight, make the linear chain, which we are end-linking into the network, make that chain longer and longer. For the precursor, P equals 0, the unreacted material, we would characterize the material with a 0 shear viscosity. At low molecular weight, the viscosity goes with the first power of molecular weight. And at high molecular weight, above its entanglement molecular weight, it goes with a 3.4 power. It turns out that all of our experiments are in the unentangled system so far, or near the entanglement molecular weight. The problem is that if the chains get longer and longer, if you make gels with precursors of higher and higher molecular weight, then the concentration of reactive functional groups are getting less and less per unit volume. You have fewer and fewer reacting groups, and you are not able to make a network anymore. The material doesn't cross-link sufficiently to reach the gel point. It always will stay a liquid if the molecular weight of the end-linking system is too large. I will come back to that in a little later. We're cross-linking long chains by connecting them on the sides, by having cross-links along the backbone. But so far, I'm just talking about end-linking system, and we have a limitation with a maximum molecular weight. We will see mostly in this range. OK, so there's a molecular weight dependence of the 0 shear viscosity. The equilibrium modulus depends also on molecular weight, and it's proportional to 1 over the molecular weight of the strands between cross-linking systems. See, the precursor molecular weight determines the strands between the cross-links in the cross-linked system. Now, at the gel point, we would like to know how S and N depend on molecular weight, or if we break S down, we would like to know how the modulus and the characteristic time depend on molecular weight. Again, we explore that experimentally. Akihiro Izuka spent some time here with us. In short, we called him Aki. He picked an interesting system here. It's a caprolactone linear chain. It's interesting for several reasons. It has a crystallization temperature at 60 degrees. It has a potential of being biodegradable with those bonds in here. So there's a potential of many things. So that's why he picked this system for the study, in addition to what I'm currently after. I'm really trying to explore the molecular weight dependence, really. So he picked precursors of different molecular weight, took a three-functional cross-linker. This is the set of parameters which we have. We have 5 different samples of basically 2,000, 4,000, 7,000, 9,000, and 20,000 molecular weight. The distribution is here about 2 mW over mn. This is the mn values which I just gave you. And the viscosity is changing with the precursor, and the fully cross-linked system is changing of that system also. Here's a typical plot of the viscosities. You can see that the viscosities are in the transition near the entanglement molecular weight. For the higher molecular weights, for the 9, this is actually PCl 9 here. For some cases, I called it 10 here. This is PCl 9. So there the slope is about 3.4, but in here it's about 2. So really going from a slope of 1 to a slope of 3.4 in this case. We are near the entanglement molecular weight, but entanglements will not play a major role in the results. The molecular weight is still too low. And the modulus of the fully cross-linked system depends on frequency, shown here, and we took the value at the lowest frequency. We really should have the value extrapolated to 0 frequency. So as close as we can get, we took the lowest value. And it's probably a pretty good estimate of the equilibrium modulus. Aki reacted the systems isothermally. This was a reaction at 110 degrees. He mixed the sample at 110 degrees using a solvent, and then evaporated the solvent, and then put the material in the rheometer. It already had started to cross-link at that time. So he found that at 110 the cross-linking rate is still low enough for our experiments. He measured 10 delta at a set of different frequencies. Here I listed those frequencies. Quite a range. It's 2 orders in magnitude. It's important to take several orders here. And he found the gel point of the material. In this case, he characterized the spectra of the material at the gel point. See, at low molecular weight, it's the slope is pretty high. We have a pretty lossy gel. And at high molecular weight, this is really PCl9 here. At higher molecular weight, this slope gets less and less, and the gel is going to be tougher and tougher. The front factor is higher, and N is lower. You can see that the front factor S is increasing with molecular weight, and N is going down, like this here. And again, there's a mirror image, not exactly mirror image, but it's still closely related. Note that N is bounded between 0 and 1, while log S really can go over the whole range. So it's not a precise mirror image, but still we capture that here in this analysis. And now Aki did something very interesting. He said, why not look at S, which is given by the modulus times the characteristic time to the N. Now, why not looking at this in terms of the initial viscosity and the final modulus? So he drew now this function. If you evaluate this with N equal to 1, then GE will settle out, and the S value is just this viscosity over here. And in the limit of N being equal to 0, this function drops out, and we have just the modulus on this side. So when N changes from 0 to 1, if this is a reasonable relation, then all the values will be on a straight line over here. And he found that, for instance, for the 7,000 molecular weight, the value at N equal 0.6, or wherever he is here, close to 0.6, coincides very nicely with this relation. So somehow he found that the strength of the material is related to the viscosity of the precursor and the modulus of the final system. Okay? And that helps us a great deal further because, remember, we're looking for molecular weight dependence. It helps us because we know the molecular weight dependence of this equilibrium modulus, and we know the molecular weight dependence of eta 0. Therefore, we can calculate the molecular weight dependence of the front factor of S. However, there's a problem. We cannot predict N. We determine N experimentally, but so far we have no capability of predicting N from first principles, so we don't know what N is. We have to find this from experiments. But still, we can find this from experimental values. Aki also changed the stoichiometric ratio of the system. The fully cross-linked system has, let me take a bigger version of this here. It has a fully cross-linked system. The modulus increases and goes to a maximum as he goes to a stoichiometric ratio of close to 1. It's a little bigger than 1 because the reaction is never driven to completion. We never get a perfect network in this type of system. And he determines the behavior at the gel point. He just has a set here, a different stoichiometry. And you can see that the slope n changes very large here, and it's smaller if he has a high, if R, the extent of reaction, is very high. And again, with stoichiometry, you see a relation coming through here. And everything fits together very nicely. In the last few minutes, let me take two data sets from the literature. If you please magnify this here, we're taking a polyurethane now in comparison. The 3-functional crosslinker, linear chain. Chambon did this in 87. And again, you see the evolution of G' and G" at different stoichiometric ratios. And you can see now the early state of the material, and then the material at the gel point, and then solidification. So this is the transition through the gel point. And here is a set of different gels with different stoichiometric ratio. This is the low stoichiometric ratio, and then this is 1 and higher. And the transition here in the off-balance system is, for the slope, is really 0.66. It's close to 0.7, this slope. And there's one more example I want to show you. In the literature, there was also polyurethane mentioned. This is a publication by Durand, De Santi, Adam, and Luck in 87. They have a nearly critical gel. Here, see, they're plotting 10 delta near the gel point, and you can see it's turning up here. They don't have flat 10 delta, so it's near the gel point. But the value here is, they're plotting actually delta itself, is close to 0.7, same value we are getting. And if you take G', G" for those material, they haven't reached the gel point yet, so the slope is still a little different between the two. And we know at the gel point the slopes have to be identical, but the slopes are really close to 0.7. And that type of large exponent is what we would expect in off-balance stoichiometry systems. And that's consistent with everything we are finding in all of our experiments. So to sum this up, we use the power law behavior to identify materials at the gel point. We can measure the effect of molecular parameters. We change molecular weight. The higher the molecular weight, the higher the front factor and the lower the exponent, so we get tough gels. And we change stoichiometry. If we have an excess of crosslinker, we have imbalanced systems, we have lossy gels, and we get higher exponents. So if we have more balanced stoichiometry equal to 1, we have a lower exponent, and the system is relaxing not as quickly. Next time I will continue on entangled gels, see what entanglements will be doing, and looking at some other phenomena. Thank you.